the last lecture, we talked about random variables. And these were, you start off with a random process like flipping a coin or picking random people, and you force it to be a number by counting or measuring something. So in the last lecture, a random variable x counts or measures something, about the outcome of a random process. And one example I gave was picking 5 random people. That's the random process. So in and of itself, when you pick 5 random people, you don't get a number. You get 5 people. But you can force it to be a number by letting the random variable x be the average of the height. Now you do have a number. So that's a general random variable. I'm going to call those regular random variables. Today we're going to talk about binomial random variables, and these are just a special type of random variable. And what do I mean by special? So binomial random variables are going to count and measure something very specific. And in particular, they're going to count the number of successes. In a fixed number of trials. So these are the 2 main requirements. One, that it's counting the number of successes. And 2, it's a fixed number of trials. In other words, you're doing the random process a fixed number of times. There's 2 other requirements, which I'll write here. The third requirement is that the trials are independent. And what this means is that when you do the random process, what happens should not affect what happens when you do the random process again. And then fourth, the probability of success should be the same on each trial. Okay, so 1 and 2 are the 2 main requirements that's most important for us. 3 and 4 are also important, but I'm going to call these the fine print. Because for the situations we're going to be talking about, 3 and 4 come almost for free. And we just have to check 1 and 2. Let me give you 2 examples. The first example is a classic example of a binomial random variable. We're going to flip 10 coins. And then x is going to count the number of heads. The random process here is we're flipping coins. We're doing it 10 times, so that's the number of trials. And x is counting the number of heads. Heads is what we're considering to be success in this case. And then another example, which is more realistic for us in statistics, is picking 20 people, picking 20 random people. Right, so the random process here is picking people. We're doing it 20 times, so we're doing it a fixed number of times. And X here is going to count the number of people who are over the age of 21. Okay, so 20 is the number of trials. And then X here is counting the number of people who are over the age of 21. So over the age of 21 is our success here. So success here means the characteristic that we're counting. In this case, over the age of 21. So I use success in quotations because it doesn't always have to be something good, right? I could also say pick 20 random people and then let X be the number of people who withdraw or fail my class, right? So that's not something good, but it's the characteristic that I'm counting. And so in this case, that would be my success. Okay, let's go through a couple examples here. So some of these are binomial and some of these are not. Part A player rolls a pair of die 10 times. Let X be the number of sevens rolled. Okay, so here rolling dice is the random process. We're doing it 10 times. That's the number of trials. So number of trials is fixed. Requirement 2 is met. X is the number of sevens rolled. So is X counting the number of successes? Yes. So here, getting a 7 is considered a success. And X is counting the number of sevens that you get. So it is counting the number of successes. So this is a binomial. Part B, a coin is tossed until a head appears. Let X be the number of tosses. Here, flipping a coin is the random process. Are we doing it a fixed number of times? No. So you're flipping a coin until a head appears, right? You don't know if it's going to be on the second toss, on a 10th toss, on a 20th toss. So we're not doing it a fixed number of times. So this is not going to be binomial. Because number of trials is not fixed. Part C, a random sample of 15 college seniors is obtained. So we're picking people here. We're doing it 15 times. So the number of trials is fixed. Is X counting the number of successes? When we're talking about people, success is a characteristic that we're counting. So is X counting the number of people who have a certain characteristic? No. Here, X is the age of the student. So X is not counting the number of people that have a certain characteristic. So this would not be binomial. Because X here is not counting the number of successes. Part D, a random sample of 250 voters is chosen from a list of 10,000 registered voters. We're picking people here. We're doing it 250 times. So the number of trials is fixed. Here is X counting the number of success. Let X be the number who support the incumbent mayor for re-election. So X here is counting the number of people who support the mayor. So that's the characteristic that we're counting. Supporting the mayor here is what's considered our success. So X here is counting the number of successes. So part D is binomial. Before we move on, let me say a little bit more about this fine print issue, requirements 3 and requirements 4 for a binomial random variable. So the main situation that we're going to be using the binomial random variable on is the situation of picking random people and then counting a number of people who have a certain characteristic. So technically, the way I'm picking these people, I'm picking the first person, but I'm not putting that first person back. I'm picking the first person, and then I'm picking the second person, and then so on. So technically, picking people that way is called sampling without replacement. And technically, sampling without replacement is not independent. And we kind of talked about this already. So remember, when we pick multiple people, you end up with multiple fractions that you're multiplying together. Okay, so let's pretend that the population has 10,000 people, and 3,000 of them support the mayor, right? So the probability that the first person supports the mayor is going to be 3,000 out of 10,000. Now, what happens on the first pick does affect what happens on the second pick. If the first pick is a person who supports the mayor, then technically for my second pick, there's actually now only 2,999 people left who support the mayor. And technically for the bottom, there's only 9,999 people left in the population, right? So what happens on the first pick does affect what happens on the second pick. So technically it's not independent, okay? And technically the probability of success is not the same on each trial, right? This is the probability of getting the first person who supports the mayor, and this is the probability that the second person supports the mayor, right? They're not the same. But for us, if your population is big enough, then if you check this on a calculator, they're actually about the same, right? So 3,000 divided by 10,000 is 0.3. And 2,999 divided by 9,999 is 0.2999299. Very close to each other, right? So as long as the population is big enough, which for our case, most of the time, actually almost all the time, the population is going to be huge, the probabilities are going to be about the same, right? So requirement 4 is almost met. And then for the same reason, they're going to be almost independent. So requirement 3 is almost met. As long as your population is big enough, which for us, almost all the time, it's going to be. There's a nice formula for finding binomial probabilities. Let me write out the formula and then we'll talk about how to use it. That's the formula. Let's talk about what these letters mean. N stands for the number of trials. The number of times you do the experiment. K is the number of successes. And then P is the probability of getting a success. And what are you trying to compute with this formula? You're trying to compute the probability of x equals k. That's the probability of getting exactly k successes. And then the way you compute it is NCK. The way you read NCK is N choose K. And then there's a formula for N choose K. N factorial, K factorial, N minus K factorial. P we talked about already. K we talked about. 1 minus P. N we talked about already. Okay, so I lied. This is not a nice formula at all. But we're going to use it one time for example 2. So one time for the culture. Example 2. Steph Curry is a 44% three-point shooter. In a game, he attempts 10 three-pointers. Part A, find a probability that he makes exactly 7 three-pointers. Okay, what is N, what is K, and what is P in this situation? N, number of trials. So how many times did he do this experiment? So the experiment here is trying a shot. 10 attempts, right? So he made 10 attempts. That's our N. K, number of successes. How many times do we want him to make it in this case? We're looking for a probability that he makes exactly 7 three-pointers. So we want him to make 7. So K here is 7. And then P, what's the probability of success? What's the probability that he makes it? 44%. So our P here is, and anytime we're doing calculations, we should convert the percents to decimals. So 44% as a decimal is 0.44. Okay. Plug into the formula. So we're looking for probability of X equals, our K here was 7. N choose K. In our case, it's going to be 10 choose 7. P to the K, 0.44 to the 7. And then 1 minus P, 1 minus 0.44 to the N minus K, 10 minus 7. Okay, so let me simplify this part a little bit. So we have 10 choose 7, 0.44 to the 7. 1 minus 0.44 I'm going to do here is 0.56. And then 10 minus 7 is 3. All right, so let me pause here and explain what we have so far. 10 choose 7, I'll talk about in a little bit. What does this part mean? 0.44 is the probability that he makes it. And I want him to make it 7 times. Okay? What is this 0.56? What does this 0.56 mean? The 0.56 we got by doing 1 minus the probability that he makes it. So 0.56 is the probability that he misses. And we want him to miss 3 times. So that's what it means for him to make exactly 7 out of 10, right? So we want him to make it 7 times, but we want him to miss the other 3. So that's what this part means. Now, what about this part? What about the 10 choose 7? So making 7 out of 10, there's many different ways that he can do that, right? So he can make the first 7, miss the last 3. He can miss the first 3, make the last 7. He can miss the first 2, make the next 7, and then miss the last 1. So there's many different ways that he can make 7 out of those 10. So in other words, there's many different places out of those 10 that he can make it. What this is calculating is 10 choose 7. How many different ways can you choose those 7 places that he makes it? Okay, so let's go ahead and calculate 10 choose 7. So the formula is n factorial. In our case, n is 10, so 10 factorial. K factorial, so 7 factorial. And then n minus k factorial, 10 minus 7 factorial. The exclamation mark, like I said, stands for factorial. Okay, so let me simplify this 10 minus 7 here first. So what we have is 10 factorial, 7 factorial, and then 10 minus 7 is 3 factorial. So what does this factorial mean? So 10 factorial means 10 times 9 times 8 times 7 times 6, 5, all the way down to 1. So basically means start with that number and then multiply going downward all the way down to 1. 7 factorial means 7, 6, 5, 4, 3, 2, 1. 3 factorial means 3 times 2 times 1. Okay? Now, there's a whole bunch of stuff that cancels out. 7, 6, 5, 4, 3, 2, 1 on top. is going to cancel with 7, 6, 5, 4, 3, 2, 1 on the bottom. So all of that goes away. And then the 3 on the bottom is going to cancel with the 9, which leaves a 3. The 2 is going to cancel with an 8, the 8, or the 10, but we'll cancel with the 8 and leave a 4 there. So what we have here is on top 10, 3, and 4. On the bottom is just a 1. Which you don't really need to write. So 10 times 3 times 4 is 120. So there's 120 different ways that you can choose where he makes those 7 out of those 10. Okay, so let's put this in a calculator. 120 times 0.44 to the 7 times 0.56 to the 3 is 0.067. That's rounded to 3 decimal places. Okay, so there's a roughly 6.7% chance of him making exactly 7 out of 3, or 7 out of 10 3-pointers. Okay, now, most of the time, I don't care about exactly something successes, right? Because most of the time, if I'm asking this question, I'm asking this question because I want to know the chance of the Warriors winning, right? So they may win if he makes 7 3-pointers, but they'll also win if he makes more than 7 3-pointers. So most of the time, I don't really care about exactly equal to some number. Most of the time, I'm looking for stuff like this. Find the probability that he makes at least 7 3-pointers. So what does at least 7 mean? At least 7 means 7 or more, right? So I'm looking for the probability of him making 7 or more is greater than or equal to 7. Right? Because if he makes 7, they'll win the game, but if he makes 8, 9, or 10, they'll also win the game, right? So if you're going to do this by hand, it's a pain because x greater than or equal to 7, to do it by hand, you would have to do it. You have to calculate the probability that he makes 7 plus the probability that he makes 8 plus the probability that he makes 9 plus the probability that he makes 10. And I'm stopping at 10 here because he's only taken 10 shots. So probability that he makes 7, exactly 7, we did already. Then you have to do it again, replacing the 7 with an 8, redo the calculation. Redo it again with a 9, redo it again with a 10, right? That's annoying. That's too much work. So we're going to do this using R, the computer. Okay, so this is the last time we'll do anything by hand here. In the last lecture, we talked about mean and standard deviation for a regular random variable. And to find the mean and standard deviation, we had to make a table. And I'm going to make up some numbers here. We had to make a table that had a p of x column, an x times p of x column, and an x minus the mean squared times p of x column. And we filled in this table using Google Sheets, and then we used the table to find the mean and standard deviation. For a binomial random variable, there's actually nice formulas for the mean and standard deviation. And this time I'm not lying. The formulas are nice. For the mean, instead of making the table, you just do n times p. That's it. For the standard deviation, instead of using the table, you can just do square root n times p times 1 minus p. See? They are nice. All right, example 3. So McDonald's has a Monopoly game where they advertise that 1 in 4 wins. In other words, you have a 25% chance of winning. So you and your friends play the game 530 times. Question is, how many times would you expect to win? Just like in the previous lecture, anytime you see the word expect, you should be thinking expected value. And expected value is just another word for the mean. So really this question is really just asking for the mean. So we do have a binomial situation here, right? We're playing this game 530 times, so the number of trials is fixed. We are interested in how many times we win, so we are interested in the number of successes. So this is a binomial situation. And to find the mean, use this formula. What is n and what is p here? N, number of trials, so number of times you played this game 530 times. P, probability of success. What's your probability of winning? 25%. As a decimal, 25% is 0.25. 530 times 0.25. 132.5. So if you play this game 530 times, you would expect to win 132.5 times. Now, say you play the game and you actually won 108 times, which is less than 132.5. The question is something shady going on here? Is something suspicious going on? Could you sue McDonald's? Say you do sue McDonald's. What is McDonald's going to say? So McDonald's is going to say this. I'll tell you exactly what McDonald's is going to say. McDonald's is going to say, look, 132.5, that's a theoretical number. So just like if you flip a coin 10 times, you would expect to have 5 heads and 5 tails. But in reality, if you flip a coin 10 times, are you always going to get 5 heads and 5 tails? No, right? Sometimes you get more than 5, sometimes you get less than 5. Same thing here. 132.5 is, in theory, you should get 132.5 wins. But in reality, sometimes you get more, sometimes you get less. You just happen to be unlucky and you got less. Right? This is normal. Nothing to worry about. Question is it really normal? Is it really normal, or is something unusual going on? So just like in the last lecture, when we're asking about unusual, I want to make the empirical rule picture. So I need the mean, which I know is 132.5. And I need the standard deviation, which I know I can get using this formula. Okay, so in this case, N, number of trials, is 530, the number of times you play the game. P, probability of success, 0.25. And then 1 minus 0.25. And then if you're using the decimal scientific calculator, just type it in exactly like this. So square root, inside the square root 530 times 0.25, parentheses, 1 minus 0.25, close parentheses, equals 9.969. Okay, and that's rounded to 3 decimal places. And then to find out the zones, the lower and upper bounds for what's considered usual and unusual, you want to make the empirical rule picture. Put the mean in the middle. And then I want to go 2 up and 2 down. So I don't really care about the 1 up, 1 down, or the 3 up, 3 down numbers. I want the 2 up and 2 down. So to jump directly to 2 up, you just do 132.5, the mean, plus 2 times the standard deviation, so 2 times 9.969. And then to go to 2 down, start with the mean, so 132.9 minus 2 times the standard deviation, 9.969. Okay, so let me do this on the calculator. So low number is 132.9 minus 2 times 9.969. 112.962. Okay, that's the low number. The upper number, 132.5, plus 2 times 9.969. Okay, 152.438. Okay, so between 2 up and 2 down, that's what's considered the usual zone. And then anything outside of that is considered unusual. So if you are outside of it, you are considered unusual. Okay, so the question is, where's 108? Is 108 in the usual zone or in the unusual zone? 108, here's 112. So 108 should be to the left. So now we'll put it in the unusual zone. So no McDonald's. Winning 108 times is not normal. It's actually unusual. So there's something suspicious going on. McDonald's is acting kind of shady. Okay, so now we're going to compute binomial probabilities on a computer using R. You can either use R that you installed onto your computer, or you can use the online R console. So I'll make sure to include a link to the online R console on Canvas and also on the lab. So R is going to do 2 things for you directly. It can do probability of X is equal to K, and it can do probability of X is less than or equal to K. If you need anything else, you have to think about it a little bit. All right, so let's jump in. Example 4, part A. A survey sponsored by the Vision Council showed that 79% of adults need correction for their eyesight. If 20 adults are randomly selected, find the probability that exactly 16 of them need correction for their eyesight. I'm going to translate this into symbols. So I'm looking for probability of X is exactly 16. Exactly 16 translated would be equal to 16. And I noticed that equal to 16 is something that R is going to do for me directly. So equal to K, I should be doing D binom. So I should be doing D binom. Number of successes that I want, so it's 16, comma, number of trials, that's the total number of people that you selected, it's 20. Probability of success, 79%. But you need to convert it to a decimal. So 79% as a decimal would be 0.79. And then you're going to type this into R, D binom, parentheses, 16, comma, 20, comma, 0.79. And our answer is 0.217. So that's rounded to 3 decimal places. Part B. The National Coffee Association reported that 63% of U.S. adults drink coffee daily. A random sample of 25 U.S. adults is selected. Find a probability that more than 17 of the sampled adults drink coffee daily. In symbols, I'm looking for probability that X is more than 17. So more than 17 translated using symbols would be greater than 17. Now, greater than 17 is not something that R is going to do for me directly, right? It only does equals to something and less than or equal to something. So the idea here is I need to translate this into something that involves an equals or less than or equals. And we're going to go with the less than or equal. So the way I'm going to do this is I'm going to make a number line with 17 on it, and some of the numbers around 17. So I really only need 1 up and 1 down. So 1 up will be 18, and 1 down will be 19. No, sorry, 16. Now, greater than 17 refers to which numbers? So greater than 17 means you don't include 17. It means the numbers are bigger than 17, which are 18 and to the right. That's what I want. Now, anytime you want something that is to the right, you need to first look at something to the left, this part to the left, which is 17 to the left. And the reason is because 17 to the left is something that I can write with a less than or equal, right? 17 to the left is less than or equal to 17, right? Less than or equal to 17 means 17 or less, or 17 to the left. So the left part is probably x less than or equal to 17, which means if I want the other side, which is just the complement, all I need to do is 1 minus that. Okay, so 1 minus that red part. So 1 minus less than or equal to 17. And that's going to tell me exactly what I need to type into R. So I need to type in 1 minus. Okay, this part less than or equal to 17 is a p-binom. Right, so p-binom number of successes is this number here, so that's 17. Number of trials, the total number of people here, so it should be the bigger number, it's 25. And then the probability of success as a decimal is going to be 0.63. And that's what you're going to type. You're going to type in 1 minus p-binom, parentheses, 17, comma 25, comma 0.63. Okay, and our answer is 0.237. And that's rounded to 3 decimal places. Part C. A new medical procedure produces side effects in 25% of patients who receive it. In a clinical trial, 60 people undergo the procedure. What is the probability that fewer than 20 experience side effects? Okay, so I'm going to first translate this into symbols. Fewer than 20. So if you need to, go back to the dictionary on the front page of the 6.1 notes that lists the phrases and also how to translate them. So less than or fewer than 20 is less than, is a less than. So fewer, less than. So this is a less than 20. Okay, less than is not one of the things that R is going to do for me directly, right? It does less than or equal, but not just less than. So I do need to draw my picture here. So I'm going to put 20 on the number line, and then I'm going to put the numbers around it, which are really just 1 up, 1 down. There's 21, 19. And what is it that I want here? I want less than 20. Which numbers are less than 20? Less than 20 would be 19 and to the left. Okay. Less than 20 does not include 20, so it's 19 and to the left. And then I'm going to rewrite this picture using a less than or equal. So 19 and to the left is really just x less than or equal to 19. And that's going to tell me exactly what, so this is what I want. And that tells me exactly what I need to type into R. So less than or equal to 19 would be p-binom number of successes is this number here, that's 19. Number of trials is the how many people total, 60. Probability of success, 25%, as a decimal is 0.25. And that's what I need to type into R. So p-binom uh, 19, comma 60, comma 0.25. And rounded to 3 decimal places, this is 0.908. Okay, so let's look at parts B and C here, and let's talk a little bit about it. So, if when you translate it, and it's not exactly one of these, if it's not exactly equals and it's not less than or equal, then you do want to draw a picture to visualize what it is that you want, right? And then your goal is to write it using a less than or equal. Okay, so this one for part C, right? I drew the picture and I rewrote that picture using a less than or equal. In part B, I drew the picture. If you are looking for something to the right, you need to look at the left part first, write that out using less than or equal, and then do a 1 minus. And that's going to tell you what you need to write. Now, this one, I'm looking for, I want the left side, right? So the left side, I don't need to do a 1 minus because the left side is exactly less than or equal to 19, and I can just type it in directly without having to do a 1 minus. Part D. Airlines often sell more tickets for a flight than there are seats because some ticket holders don't show up for the flight. An airline estimates that 90% of ticket holders actually show up for the flight. If the airline sells 50 tickets, what is the probability that no more than 46 of the ticket holders will show up for the flight? Okay, so I'm going to translate into symbols. No more than 46. What does that mean? So this one is one of the ones that I have to think about a little bit. So no more than is a less than or equal. All right, so you need to use this dictionary. No more than is a less than or equal 46. Now, lucky for us, less than or equal is exactly one of the things that R is going to do for us. Okay, so less than or equal, I just need to do P binom. So we just need to do P binom number of successes, that's this number, 46. Number of trials, that's total number, the bigger number, so that's 50. Probability of success, that's going to be 90% as a decimal, so that's 0.90. And then we just need to type that in. P binom 46, 50, 0.90. Okay, rounded to 3 decimal places, this would be 0.7, that's going to bump up to 50, so 750. Part E, suppose that 63% of people are right-handed. If 30 people are randomly selected, what's the probability that at least 15 of them are right-handed? Okay, so translated, this would be at least 15. At least 15 on my dictionary. At least is a greater than or equal to. Okay, so we're looking for greater than or equal to 15. Okay. So greater or equal is not one of the things that R is going to do for me directly. Right? It only does equals and it only does less than or equal. So I do need to draw this picture out. I'm going to put 15 in on my picture and then the numbers around 15, which is just 1 up, 1 down. You can put more numbers if you want. Now, what is it that I really want here? I really want greater than or equal to 15, which means 15 and to the right. That's what I want. Anytime you want something to the right, you need to look at the left side. So the left side here is 14 and to the left. And then write that using a less than or equal. So 14 and to the left will be written as less than or equal to 14. And then to get what I want, which is the complement, I just need to do 1 minus that. So my answer that I want is 1 minus less than or equal to 14. And what I'm going to type in is 1 minus less than or equal is a P binom. So we're going to do P binom number of successes is this number, that's 14. Number of trials, total people here is 30. Probability of success here is 63%, as a decimal 0.63. Okay, so I'm going to type in directly 1 minus P binom. So 1 minus P binom, parentheses, 14, 30, 0.63. Okay, my answer 0.950. So that's rounded to 3 decimal places. Yeah, that 49 is going to go up to 50. Okay. F. Of all the registered automobiles in California, 8% fail the state emissions test. 12 automobiles are selected at random to undergo emissions tests. Find a probability that at least one of them fail the test. Okay. At least one. So we just talked about an at least 15, so that's going to be a greater than or equal to 1. All right, so it should be the same idea as part E. Greater than or equal is not one of the things that R is going to do for me directly, so I need to draw a picture to help me visualize. 1, numbers around 1, so 2, 0. Greater than or equal to 1 refer to which numbers? So greater than or equal to 1 is 1 and to the right. So that's what I want. Anytime I want something to the right, I need to look at the left side first. So the left side is that piece, that red piece. And the idea here is you're going to write that red piece using a less than or equal. So 0 to the left is less than or equal to 0. And then to get what you want is the complement. So it's just 1 minus that. So 1 minus probability of x less than or equal to 0. And what I should type in is 1 minus less than or equal is a p-binom. So we're going to do p-binom. Probability of success, it's that 0. Number of trials, so total number of cars here, we're talking about 12 total. And then probability of success is 8%. So be careful, 8% as a decimal is not 0.8. Right, so you move decimal 2 to the left, so 2 to the left will be 0.08. And that's what you'll type in. 1 minus p-binom uh, 0, 12, 0.08. And 0.632. Okay, and then finally, let's go back to example 3. So this is the McDonald's acting shady one. Okay, and let's actually calculate. So we already said that we think winning 108 times, winning only 108 times is unusual. So that something is strange is happening here. But let's actually calculate what's the probability of winning 108 or less. Okay, what's the probability of winning 108 times or less? So what I'm looking for here is probability 108 or less is just less than or equal. Lucky for us, less than or equal is exactly one of the things that R is going to do directly, so I don't need to draw a picture and rework it. So I just need to do p-binom. Probability of success is that 108. Number of trials. This was back in example 3. Number of times we played this game was 530. And then probability of success. So McDonald's is saying that the probability of winning was 25%, so it was 0.25. And let's see what this is. P-binom 108, 530, 0.25. And rounded to 3 decimal places, this is 0.007. Okay, so McDonald's was saying that, you know, sometimes you win more than 132, sometimes you win less, right? Winning 108 times is normal, right? Sometimes you're higher, sometimes you're less. We were just unlucky and we won less. So McDonald's is saying this is normal. So we said that, no, 108 is unusual. And even more, now we can say how unusual it is to win just 108. We're saying that it should only happen this as a percent is 0.7%. What happened to us should only happen less than 1% of the time. So not only is it unusual, it is highly unlikely that we should win only 108 times. So McDonald's is acting kind of shady here. All right, so that's it for today. Have a great day. Talk to you guys later.